So if you've got two particles and some distance r between them, the potential energy we're talking about is the energy as a function of r. So as they get closer together or further apart, the potential energy changes. And we typically measure that distance in units of sigma, because this is going to be some absurdly tiny number of meters if we were measuring it in meters. So instead, we typically measure it in units of sigma, where sigma is the diameter of one atom. So sigma, so that's epsilon. Sigma, there we go. So sigma is the distance, the diameter of one atom. And we're typically going to be measuring r in units of sigma, as if that were, I mean, that is a unit of measurement in terms of distance. So we would describe r as some number of sigma, like maybe 4.7 sigma apart from each other or something. And a special distance in particular is the distance where they're at equilibrium. The idea is if the particles were so close they were actually touching, in that case, what would be the distance from center to center? Yeah, center to center is 1 sigma, because from center to the edge would be 1 r, or 1 radius, half of sigma. From the edge to the next center would be another half sigma, so that would be 1 sigma apart. But if the particles are so close they're effectively touching, what are they going to be doing to each other? Yeah, they'd be repelling because the electron clouds are too close. So they'd repel. Equilibrium, where attraction and repulsion balance out, is a little bit further apart than that. So the equilibrium distance, which we call r naught, is half sigma plus a little bit extra. So that occurs when we're a little bit more than 1 sigma, specifically about 1.12 sigma. And we call that r naught, r sub 0, that is the equilibrium distance. And that is a value of r, but we typically use r to represent the distance at any distance, a variable, but r naught is a specific value of r where something important happens, specifically where they're at equilibrium. And when they're at equilibrium, what do we know about the potential energy? Not 0 in this case, because we can have, 0 is kind of just a reference point. But ignoring the numbers, what should we expect so no numbers at all, just what would we expect about the potential energy at equilibrium? What kind of value would we expect? Yeah, equilibrium is the lowest potential energy. Formally, equilibrium is the location where the forces balance out. That is where force is 0. There might be attraction and repulsion, but they balance out when the particles are this far apart. And how does force relate to the potential energy graph? Right, force is the derivative of potential energy. Specifically the negative of the derivative, but if it's 0, it doesn't matter whether it's positive or negative. So at equilibrium, the location or distance where force is 0, the potential energy has to have 0 derivative. And what kind of point on the graph has derivative 0 at that point? If you think back to calculus, if you set the derivative of a function equal to 0, what sort of point are you trying to find? Yeah, a min or a max. And in this case, it will be a minimum. So locations where the force is 0 are going to be critical points for potential energy, either a max or a min. In this case, it will be a minimum. So potential energy is at its lowest at that point, or at that distance. We're not really talking about locations here. R doesn't represent locations. R represents how far apart are the particles. Yeah, go ahead. So if we call that distance R naught, that's where we're going to expect to find the lowest potential energy. And the way we define potential energy here, we set 0. We're going to get an asymptote here. We define 0 as the asymptote. That is, 0 energy is the asymptote. So we're going to end up with, like that. Say something like this, where we hit the lowest possible point at R naught, and then curving up, something like that. It's not exactly accurate for the shape, but pretty close to it. So we have the lowest, some lowest value of energy, and we typically call that negative epsilon. So this energy value we'll call negative epsilon. So epsilon is a quantity of energy, essentially a unit of energy. It is positive, but the value here is negative, so we'll call this negative epsilon. Negative epsilon. So that's, or if we write out energy in terms of epsilon, if we think of epsilon as a unit of measurement, we could just call this -1. But keep in mind that means -1 epsilon, in the same sense that R naught is 1.12 sigma. So that would be our characteristic shape of the potential energy graph of these two particles. Any questions on that so far? Also on this graph, what's the lowest the total energy could possibly be? Yeah, -1 epsilon. Because if the total energy is -1 epsilon, if we put in a horizontal line for total energy, because we should assume total energy is constant here. So if E total is exactly -1 epsilon, in that case, what do we know about the kinetic energy graph? What would the kinetic energy graph look like if E total is the lowest it can possibly be? What would be the value of kinetic energy at R naught here? Yeah, at that location, kinetic energy would be 0, because potential energy equals kinetic energy, or potential energy equals E total there, so there's no difference. So at that location, kinetic energy is 0. If we go to the left or right, potential energy would increase. So what would have to happen to kinetic energy? If you go to the right, potential energy increases, and therefore kinetic energy would decrease. But that can't happen because kinetic energy can't be negative. So that means these particles can't get further apart, because that would lead to negative kinetic energy, which doesn't make sense. They also can't get closer together, because that would also lead to negative kinetic energy. So these particles, if the total energy is -1 epsilon for this system, the particles are at rest at equilibrium. They're not doing anything. They're just sitting there and not moving. So this represents the lowest possible energy this system can have. And it's not really very realistic. We wouldn't expect atoms to just be sitting there and not vibrating at all. If we raise E total, then we're going to get some new values of kinetic energy. Specifically, we're going to expect kinetic energy to be 0 at these new intersection points. So here and here, at the two R values where potential energy meets E total, kinetic energy would be 0. And what would you expect kinetic energy to look like in between those points? within this value, between these points, what would you expect the kinetic energy graph to look like? Yeah, it's ultimately going to be a reflection of potential energy. Because if you actually solve for kinetic energy, we know E total is kinetic energy plus potential energy. If you isolate kinetic energy, you get negative potential energy plus E total. Potential energy is a graph of this curved shape. Negative potential energy would be that graph flipped upside down. So if we take the potential energy graph, but only this portion of it, flip that upside down, and it's also going to flip up to here, flipping across, reflecting across the axis. And then plus E total, that's plus a constant, so that's just going to shift it. And then we would also cut off anything below the axis because kinetic energy can't be negative. So we are taking, you could think of it as taking the entire shape of the potential energy graph. The negative sign flips that upside down. So the exact reflection. And then plus E total, that's adding a negative, so that shifts the graph down. And then we cut off everything below the axis. And what's left is the kinetic energy graph. So that means the particles are at rest when they are this close together, and they're at rest when they're this far apart, but they're able to move around. They're able to have speed while they're in between those. So they can get this close together, this far apart, R min and R max, the minimum distance, maximum distance. But they're oscillating. They can oscillate between this close together, this far apart, oscillating back and forth, going fastest when they're passing through equilibrium. So this would be one possible state of the system. At this low energy, the particles are oscillating, and we'd say they are bound together. They're in a bonded state because they can't leave each other. They can get this far apart, but then they bounce back in. Any questions on that so far? How can we modify this so they are not bonded together if we want them to be able to continue for moving further outwards and not bounce back in? What would we need to do to the system? Or to put it more mathematically, what could we do to this graph? How could we modify that to allow the R max to extend outwards forever, to allow them to just keep moving further and further apart, rather than having this hard boundary on how far apart they can get? Yeah, we could increase total energy. So if we were to increase E total to, let's say, this level, then that's going to change R min and R max. And our new kinetic energy graph is now going to look like a reflection of this portion of the the potential energy curve. So it'll be this region flipped and shifted and cut off at the axis. So this would be our new kinetic energy graph. The particles are able to get a little closer together, a lot further apart, and also they're traveling faster as they pass through equilibrium, so larger and faster oscillations. But if we want to truly break the bond, because this is still bonded, they still can only get out to a certain point and then they fall back in. What do we have to do, or how high do we have to raise the energy to break the bond? To allow the particles to move further and further out forever? Yeah, if we bring E total all the way up to 0, if E total is 0, let's see what the graph looks like. So if we bring E total up to 0, then for our kinetic energy graph, again, we could think of this as tracing the potential energy graph. Flip that across the axis. Something like that, I guess. Flip it across the axis. But then we don't need to shift it at all. We just reflect it and don't shift it because we're adding 0. E total is 0, so there's no shift. It's just a reflection. And of course, then we need to cut off everything below the axis. So get rid of everything below the axis here. And this is our new kinetic energy graph. There's still an R min. There's a closest they can get together. So there is a minimum distance. If they're going towards each other, they hit that distance and then bounce back off. But there's no longer a maximum distance. The kinetic energy graph now has an asymptote instead of hitting 0 at some point. So that means they can keep getting further and further apart. They do get slower and slower and slower, but they never come to a stop. So at this point, once total energy has reached 0 for this pair of particles, we'd say we have broken the bond. These particles can now just keep getting further and further apart without any limitations. Any questions on that so far? So overall, from that lowest possible energy up to just barely breaking the bond, how much energy did we have to add to make that happen? Specifically one what? Yeah, 1 epsilon. This is actually a very good way of thinking about epsilon. Epsilon is often described as the depth of the energy well, but you can think of that as how much energy you have to add to break out of that well. Epsilon is the amount of energy required to just barely break the bond, or to guarantee breaking the bond. It might take less energy than that. Maybe the particles already have some energy. But if you want to guarantee breaking the bond, you would add plus epsilon. If you add more than that, you're able to bring this graph even higher, which means that the particles are able to not only get further apart, but continue at a fairly fast speed. They have more kinetic energy and therefore faster speed as they're traveling apart. So if you add exactly epsilon, that's enough to just barely break the bond. Any more than that, and you've broken the bond and allowed them to be moving fairly fast. But epsilon is enough. 1 epsilon is enough to guarantee just barely breaking exactly 1 bond. So that's a very useful way of thinking about epsilon. Any questions on that so far? Or what if we were dealing with more particles? Let's say instead of just 2 particles, let's say we had a third particle arranged in a triangle. If we had a cluster of 3 particles and we wanted to shatter that cluster, how would we figure out how much energy we'd have to add to break up this cluster of particles? It might help to label these. Let's call these particles A, B, and C. Yeah, we want to break all the bonds, right? And the nearest neighbors thing, I think, is going to be more applicable to larger clusters. In this case, there's only 3 particles, so we can just deal with the bonds individually. What bonds do we need to break if we want to split this up? Like, which particles are connected to which other particles? Yeah, we've got bond AB, bond AC, and bond BC. There are 3 bonds, so we need to break 3 bonds, which means we'd add how much energy? Yeah, to break these bonds, we must add plus 3 epsilon to the system. So we would say that the delta energy would be plus 3 epsilon if we want to break the bonds. However, to describe how much bond energy it actually has, if it's in the unbonded state, like let's say we have these 3 particles that have been broken up. Let's say we split up the system and so we add some energy, time passes, And we now have particle A, particle B, and particle C far apart from each other. In that case, where they're unbonded, we've added enough energy that the whole system is now unbonded. So that transition requires plus 3 epsilon worth of energy. How would you want to describe the amount of bond energy in an unbonded system? If we got these particles that are not interacting, how much bond energy would you say they have? Yeah, we'd want to describe this as 0 bond energy. In general, if the particles are not bonded together, if they're not interacting at all, we want to say the bond energy of that system is 0. And by the way, what phase would you say this material is in if the particles are not interacting at all? Yeah, this would be a gas. Whereas if they are bonded, presumably this would be, what phase would you say that's in if they're bonded together like this? Liquid? I think in this case I would call it a solid. A liquid is sort of an in-between situation where the particles have some bonds. You've had enough to go from solid to liquid, you add enough energy to break some of the bonds, but not all of them. So they're able to move more freely, but they're still stuck to each other. Whereas, so going from solid to liquid means you're breaking some of the bonds. Going from liquid to gas means you're breaking all the rest of the bonds. But in this case, let's say this is something that sublimates. It just goes from a solid directly to a gas. You have to add plus 3 epsilon to make it into a gas, which has 0 bond energy. Before you added the energy, how much energy did it have? Yeah, it had to have had negative 3 epsilon. So in a bonded state, if you're talking about a solid or liquid, bond energy is actually a negative value because you have to add energy to bring it up to 0. This goes back to the same idea that in a bonded state in the LennardJones potential energy graph, E total is negative if the situation is bonded. You'd have to bring it up to 0 to break the bonds. Same idea here. Unbonded, we treat bond energy as 0. Bonded, we treat bond energy as having a negative value. You could think of this as each bond has a negative amount of energy, specifically negative epsilon. So this bond has energy negative epsilon, this bond has energy negative epsilon, this bond has energy negative epsilon. If you want to break the bonds, you have to add 3 epsilon to destroy those negative amounts of energy. Or if you want to make it bonded, if you want to condense the solid into, or condense the gas into a solid, how do you create these bonds? What do you have to do to turn the gas into a solid? In terms of energy transfers. Like if you've got carbon dioxide and you want to turn it into dry ice to go from gas to solid, what would you have to do? Yeah, you've got to remove energy. So removing energy allows bonds to form. And it might seem kind of counterintuitive that you have to reduce the energy to create bonds. But the reason for that is that each bond has a negative amount of energy. So to create a negative amount of energy for the bond, you have to introduce a negative change in energy to the system. That is, you remove energy to allow these negative energy bonds to form. And the negative in this context just means less than the value we're calling 0. We're declaring the unbonded state to be considered 0 bond energy. So anything with less energy than that is going to be a negative amount of energy. So in any bonded state, solid or liquid, bond energy will be a negative value. In the gas phase, an unbonded state, bond energy will be 0. Delta energy could be positive or negative depending on which direction you're going. So going from bonded to unbonded, you're adding energy. Going from unbonded back to bonded, you're removing energy. But in general, in any bonded state, E bond will have a negative value. Typically negative some number times epsilon. Any questions on that so far? And generally, epsilon will be some number of joules. It'll typically be very, very small, like just something times 10 to the negative 21st joules, for instance. But we usually write these formulas in terms of epsilon, partly because it's easier to write than 10 to the negative 21st joules, or whatever it happens to be, but also because different types of atoms can have different values for epsilon, different amounts of energy per bond. By writing the formulas in terms of epsilon, they can apply to any atom, and then we can substitute in the exact value for epsilon for a particular type of atom when we need to. Any other questions on that so far? Then let's try adding in one more particle and see what happens. Let's say we put in one more particle. Let's call this particle D. Where could that particle be placed in order to be in equilibrium with as many other molecules as possible, or as many other atoms as possible? Can I get D connected to all the other particles? Yeah, if we put this on top, because we can treat this as three-dimensional. If we put this on top, making sort of a three-dimensional, four-corner pyramid, a four-sided die, then D can now be connected in equilibrium to all four of these. We've got a connection from B to D, and from A to D, and from C to D, forming this four-cornered pyramid. And in that case, how many bonds are we now looking at? Yeah, this pyramid, tetrahedral pyramid, has 6 bonds. So E bond is going to be, each one has negative epsilon worth of energy, so E bond is negative 6 epsilon. In other words, if you wanted to shatter this, if you wanted to split it up into individual atoms, making it a gas, you'd have to add plus 6 epsilon to make this happen, because you'd be breaking 6 bonds to do it. Any questions on that so far? And then for larger systems, if you're dealing with not just a few particles that you can actually count up, let's say you're dealing with maybe lots and lots and lots of particles, it can be inconvenient to manually count up all the bonds if you've got a very large number of particles. So instead, we got to use techniques from mathematics, specifically from combinatorics, to determine how many bonds there are if we know how many particles there are. And let's start with this small example again. We have 4 particles. If we wanted a way to predict how many bonds there are without actually counting them up, like here we can just count 1, 2, 3, 4, 5, 6, there's 6 bonds. We could even list them, A to B, A to C, A to D, B to D, B to C, and so on. But if we wanted to mathematically predict how many bonds to expect without counting them up, one way to do that would be to look at a typical particle. Like all these particles are behaving the same. Like A, for instance, has how many bonds attached to it? Yeah, A has 3 bonds, A to B, A to C, A to D. How many bonds does C have? Also 3. C is connected to the other 3 particles. We've got complete symmetry here. Each one of these particles, each corner is connected to the other 3 corners. So we can say there are 4 particles, each one has 3 bonds. So if you got 4 particles and 3 bonds per particle, mathematically, what could you do with those values to get the total number of bonds? Yeah, if we multiply and check the units on that, 4 atoms times 3 bonds per atom, the atoms and atoms cancel out, so we end up with bonds. So 4 times 3 would be 12 bonds. Does that match the number of bonds we counted? We have 12 bonds. Because when we counted them, we had 1, 2, 3, 4, 5, 6. That looked like only 6 bonds. So why is it that multiplying 4 times 3 gets us 12 instead of these 6 bonds we can actually see here? Because it's true that there's 4 atoms, and it's true that there's 3 bonds per atom. So why is there this discrepancy? Yeah, we counted some of these bonds twice. If we look at these bonds one at a time, let's say we're talking about, let's say we start with A. A has 3 bonds, 1, 2, 3. And B also has 3 bonds. B to A, that's 1. B to C, that's 2. B to D, that's 3. But note that we've already counted one of those twice. And if we continue this, if we say C has 3 bonds, C to B, C to A, C to D, and likewise D has 3 bonds, D to B, D to A, C to D. So in that case, if we say that each particle has 3 bonds, that's true, but that also counts each bond twice. Yeah, exactly. We're counting A, B as a bond. We also just counted B, A as a bond. But that's not really 2 different bonds. A, B, and B, A are the same bond. So how do we undo that? How do we modify our mathematics here to account for that double counting? Yeah, all we need to do is divide the result by 2. So 12 divided by 2, to account for the fact that we just counted twice as many as we should, gets us 6 bonds, which is the actual result that we should be getting here, based on manually counting them up. So we can often use this as an approach to find the total number of bonds, at least bonds of a certain type, in a larger cluster. Like if we had hundreds of bonds or thousands of bonds or trillions of bonds or particles, many particles, but we know how many bonds each particle has, then it becomes much easier to predict how many bonds we can expect in total. Any questions on that so far?
Yeah, I have a question. So when we're finding the total number of bonds for like an item with a lot of particles, should we just count the number of particles and multiply that by how many bonds each particle have and then divide it by 2?
Yeah, as long as and the thing is sometimes that approach doesn't end up double counting. So be careful with that. Usually you will need to divide by 2 to eliminate double counting. But I would recommend always checking, like go through like the process we just did. We say A has 3 bonds and mark them down, and then say B has 3 bonds and mark them down, and notice that we just counted one of them twice. So always check if the process you're doing really does count a bond twice. If it does, then you need to divide by 2.
Okay, yeah, thank you.
You're welcome. Let's add in one more particle, or actually, instead of adding in one more particle, let's keep the same 4 particles. But let's move them around a little bit. Let's say instead of 3-dimensional tetrahedral pyramid, let's say we're in a 2-dimensional situation. Let's say we're only in 2 dimensions, and these particles form into a square shape for other reasons. Maybe there's some sort of crystal structure going on due to the way the particles interact with each other. In that square shape, how many bonds do we have? We should still expect each of the 4 particles to be interacting with the other 3. So we should still expect 6 bonds in total. But how many of them are actually equilibrium distance from each other? For instance, D is equilibrium distance from which other particles? Yeah, it looks like each one just has 2. Yeah, D to, the thing is D to C is further. I would expect the adjacent neighbors, D to A and D to B, those would be equilibrium distance from each other. Those would be 1.12 sigma, in other words, R naught. And likewise, A and C and B and C. These I would expect to be equilibrium distance, 1.12 sigma. But the other bonds, like the diagonals D to C and A to B, those aren't the same distance. Those ones are longer distances. So if we wanted to account for those as well, we would say, to begin with, we'd say there are 4 nearest neighbor bonds. And in this case, we can manually count those up: AD, DB, BC, and CA. So there's 4 nearest neighbor bonds. And what would you expect the bond energy of each one of those to be? If they're equilibrium distance from each other, how much energy does each bond have? What's the symbol we use for the energy of one bond? Yeah, that's the negative epsilon. So 4 nearest neighbor bonds at energy -1 epsilon each is -4 epsilon. So -4 epsilon is the energy of just these 4 bonds. That is, if you add 4 epsilon, that would be enough to break these 4 nearest neighbor bonds. But we also need extra energy to account for these diagonal bonds. So how could we figure out how much energy one of those diagonal bonds has? Can you figure out the distance from D to C? Yeah, we can use Pythagorean theorem here. If we take a look at these side lengths, let's say we make a right triangle. Using this right triangle here, we know the side lengths of the edges of the square are going to be R naught. So we can say this is R naught, this is also R naught, and the hypotenuse, let's call that capital R. So based on Pythagorean theorem, we could say R naught squared plus R naught squared equals capital R squared. Leg squared plus leg squared equals hypotenuse squared. And then if you solve that for big R, what would you get? First of all, what's R naught squared plus R naught squared? Yeah, that becomes 2 R naught squared. Then we take the square root, we get square root of 2 times R naught. So that means R, the distance across the diagonal, these opposite corners, is going to be square root of 2 times R naught. And you could look that up on the graph. If you want to know approximately how much energy that has, square root of 2 is 1.4-ish. So you could take 1.4 times R naught, or if this is marked in units of sigma, you could take 1.414 times 1.12 sigma and get a new value on the graph. So you find that value on the graph. Let's say that's about here-ish. So let's say this is 1.4 R naught. And then you can use the graph to find how much energy it has at that distance. So this distance, and you want a more accurate graph than this sketch, but that distance should have this much energy. And I'm just approximating here. Let's say we find that that's about 0.2 epsilon, or negative 0.2 epsilon. Then we could say there are nearest, or we would probably call these the second nearest neighbor bonds. And it looks like there's 2 of them, D to C and A to B. So we've got 2 second nearest neighbor bonds. And based on the graph, and again, this is just a very rough approximation. You want to use a more accurate graph than this. Looks like it's about negative 0.2 epsilon. So we can multiply those together. We've got two bonds of this type. We know the energy of each one. So 2 times negative 0.2 would be negative 0.4 epsilon. So that's the energy of those two diagonal bonds. And it looks like we now have all the bonds involved here. There's 4 nearest neighbor bonds, 2 second nearest neighbor bonds, and that's it. Notice that that accounts for all 6 bonds we should expect. And then how would we use that to find the actual bond energy here? Yeah, add those together. Negative 4 epsilon plus negative 0.4 epsilon would be negative 4.4 epsilon. So this cluster, this square of atoms, has a total bond energy of negative 4.4 epsilon, in the sense that you'd have to add 4.4 epsilon to split it up completely. Any questions on that so far? Then let's try a quick example where we are talking about a much larger cluster, just to see what that's going to look like. If you're dealing with a much larger cluster of particles, let's say hundreds and hundreds and hundreds, or really more realistically, you'd have something more like around Avogadro's number of particles. But for simplicity, let's assume you're dealing with just maybe 1,000 atoms in a rectangular grid like this. So let's say you've got a square grid, equally spaced. So just like the square we were talking about, except lots of them. So let's imagine this just continues for a very long distance in either direction. And for simplicity, let's still assume 2-dimensional. So if this square grid just keeps going for a very long distance in either way, if we want to find the total bond energy, and let's say we've got 1 million atoms in a square grid, so 1,000 by 1,000. And we want to know what's the bond energy of this cluster. In that case, there's no way we'd be able to count up all the bonds manually like we did here. Instead, we want to use the combinatorics ideas to predict how many bonds to expect. So to do that, I would recommend choosing a typical atom to start with. Let's say we focus on this atom as our example. How many nearest neighbors does that atom have? That is, how many other atoms nearby are equilibrium distance from it? 4 or 8. It might, if you're having trouble visualizing which one it is, it might help to imagine this circle or sphere expanding outwards from the atom equally in all directions. So if you expand this circle outwards, the first time this circle is going to hit other atoms, how many other atoms does it hit? It is expanding outwards equally. Yeah, those 4 atoms that the circle just hit are all, by definition of a circle, are all equidistant from the center. The circle is just all points that are the same distance from the center. So those 4 atoms are the nearest neighbors, which means this central atom, this typical example central atom, has 4 nearest neighbors. So each atom, a typical atom in this cluster, has 4 nearest neighbors. And each of those would be at an energy of negative epsilon. If we expand this further outwards, though, it next is going to hit, looks like 4 more that are slightly further apart. And notice that it hits those 4 before it hits any others. So these 4 would be the second nearest neighbors. And they're on diagonals in the same way as the ones we saw earlier. So what's that distance? It's not doubled, because doubled would be like if we went from an atom to R naught and then another R naught further. So the green distance is much shorter. It's definitely longer than equilibrium, but it's shorter than twice as much as equilibrium. But what distance did we get for that diagonal in the previous example? In terms of energy, it was negative 0.2 epsilon, yeah, or approximately negative 0.2. By the Pythagorean theorem, this is going to be another square root of 2 times R naught. So square root of 2 times equilibrium distance, because we have a right triangle here we can use. You can, in general, as long as you can establish straight line distances and find some sort of right angle, you can use the Pythagorean theorem, or more generally, other results from trigonometry in order to find the diagonal distances. In this case, that's square root of 2 times the equilibrium distance. Look that up on the graph. And again, this is just an approximation. I'm going to say about negative 0.2 epsilon each, as opposed to the nearest neighbors, which were negative 1 epsilon each. The second nearest neighbors, it looks like this typical atom has 4 second nearest neighbors at negative 0.2 epsilon each. But we're not looking at just this one atom. We want to know the total number of bonds. So if there's a million atoms and each one has 4 nearest neighbor bonds, how would we find the total number of bonds of that type? Four bonds per atom and a million atoms. What do we do with those values? Yeah, we can multiply those together, because this is 4 bonds per atom. We multiply that by 1 million atoms. But also remember, if we say this atom has 4 bonds and this atom has 4 bonds, we're counting each of those bonds twice. So what else do we need to do? Yeah, divide that by 2. So we actually get 4 times a million divided by 2. That's 2 million bonds. I'll just write that as 2 capital M, 2 million bonds at negative 1 epsilon each. So 2 million times negative 1 epsilon, that's negative 2 million epsilon. So negative 2 million times epsilon is the energy of all of the nearest neighbor bonds. But we also want to, that alone would be a reasonable approximation. The second nearest neighbors don't contribute all that much extra beyond that. But we could be more accurate by including the second nearest neighbors. Again, there's 4 second nearest neighbor bonds per atom. So just the same, we can multiply it by the number of atoms, 1 million atoms. Divide by 2 to eliminate double counting, because for instance, if we also say, let's say this atom has 4 nearest neighbor or second nearest neighbor bonds, we just counted this one twice. So we still need to divide by 2. That gets us 2 million second nearest neighbor bonds. Each one of those has negative 0.2 epsilon as the energy. So 2 times negative 0.2 would be negative 0.4 million epsilon. Add those two, or sorry, negative points. Yeah, that should do it. Negative 0.4 million epsilon. Add those up, and we get E bond of this whole system. This enormous system would be negative 2.4 million epsilon. And then epsilon itself is going to be some absurdly small number of joules. So you might plug that in and simplify that as well to get a result in joules. And even that's not going to be exact. We're ignoring, for instance, the third nearest neighbors, the fourth nearest neighbors, the fifth nearest neighbors. But generally, by finding the nearest neighbors and second nearest neighbors, that's going to be a pretty good estimate, because the third nearest neighbors and beyond contribute very little to the energy. Any questions on that? All right, then try that out with some other examples on your own. I think that general approach should work pretty much anytime you got some small or large cluster of particles and you're trying to find the bond energy. For small clusters, I would recommend counting up the bonds manually and addressing each type. For larger clusters, categorize them if you need to consider nearest and second nearest, but find ways from combinatorics to predict how many bonds total of that type, because there's no way you'd be able to count them all up manually. Use combinatorics to find a formula for how many. So give that a try. Let me know if you have any other questions, and I will see you next time.